Afternoon, everyone. Welcome to the week five live session. That is the problem solving session for the course Ultrafast Laser Spectroscopy, which is taught by Professor Anindya Datta from IIT Bombay, and I am one of the teaching assistant for that course. My name is Nikita Mahajan. As we have been doing this since the last 4 weeks, and we have come to the week five. As previous modules, in this week also, we'll be discussing some of the important questions which were given in the assignment 5. Going on with this, since it's the time now, I'll not like to waste the time and just start the session. So first of all, I'll be sharing my screen so that if the incoming people, whoever join this session, they are able to see whatever we are going on with. Yeah. So first of all, in this week, there are some important concepts which were discussed that are related to the active and passive modulating and the other things. And with this, we come to the first question. Upon increasing the modes locked together in to produce the pulse laser beam, the resultant repetition rate and the pulse width respectively increases. The options for this question are increases and decreases and increases, remains the same and decreases, and decreases and remains the same. So first of all, earlier we had studied what is a modulated or mode locked beam. Okay, so first of all, I'll give a quick revision to whatever we learnt in the last session. So what is a mode locked beam? That is like, suppose you have a gate like thing. uh, Okay, just a second, I'll take a pen. Suppose for the pulse laser beam, what is a pulse laser beam? First of all, which does not have a which is not a continuous wave. That is, with the time intervals, it increases and then it decreases in the intensity. Okay, and then again its intensity turns to zero, and then again it increases to a maximum and then turns zero. So with respect to time and intensity, it is just plotted like this. So first of all, with respect to intensity and time, this is a pulse laser beam. Okay, yeah. Now, what we talked about, uh, beam mode locking, what we say is, suppose in a particular mode, say there a particular laser, there are n number of modes, and what we want to say is the n number of modes signifies that, although suppose we are working on the laser which has a wavelength of 405 nanometer, but actually it has, like, it will not have a value maybe beyond 440 or something, but there will be a range like this. Okay, so like this, we have a lot of modes in a particular, say, which are very close to each other but still are different from each other, say lambda, or the other one is lambda plus 1, the third one is lambda plus 2, and there is like, or lambda plus x or something, like there is a small increase or decrease, or they vary with each other in somewhat terms. So for this, we had studied that how to mode lock a laser when you just say this is the pulse and you are allowing it to pass through a gate, and that too you are managing them so that there is a zero phase difference. That is, the phase difference between them is equal to zero as a function of time. Then you are able to get a sequence, or you are able to get n number of phases which are mode locked to each other. Now the same case, we had deduced some equations which were related, or which from which we could deduce what is the relation between the number of modes and the repetition rate and the pulse width. So first of all, I'll try to rub this because it will become a bit messy. Yeah. So the first direct relation which we could get was, here, let's say here we have a diagram. Okay. Now these are the mode log pulses. So with respect to the intensity, the pulses which are mode log, they are not entirely like, then too they have some lower frequencies and then they increase to some extent and then reduce to zero. So this is the intensity with respect to time graph for the pulse. From this relation only we can deduce the relation, that is the TP. What is this TP? This TP is the repetition time. Repetition time for the pulse. Suppose this pulse comes in a time of say 20 picoseconds, the other pulse will repeat itself in the, okay, not in picoseconds, we can say this pulse repeats itself in every 10 nanoseconds, and therefore the TP will be equal, like the TP is the sorry, the TP is the pulse width, which depends on the number of modes also. So what is pulse width? Pulse width is the time period for which our laser beam is just gets on and off. That is the time period for which the pulse exists or remains. So related to that, the equation which we derived was Tp, that is the pulse width, is equals to 2L upon C. Okay. And similar to this, we had some other relation related to, okay, sorry, related to this, the pulse width and the repetition rate. So that was T is equals to 2L by C. Okay. Here L is, suppose this is the total length of the cavity from where the rays are going to and fro throughout the cavity. So this is the length of the cavity which is denoted by L. So what is L? L is the length of, yeah, length of cavity. Got it? The second thing is, the second thing is C, which is the velocity of light. Okay. And the pulse with TP. So here only in the next slide what we got to know is TP, that is TP has a relation, what the relation it has is 2L upon NC. Okay. So here is the relation with the TP. So TP is equals to 2L upon NC. Here the new factor that comes into play is the N, which is the N is equals to number of modes. Number of modes in what? Number of modes in the mode log laser beam. Okay, just a second. So here n is the number of modes. The writing in OSC is, wait, let me just write it on a fair page. Yeah. So first of all, what I told you, what is a mode log laser? Mode log laser is some in which there are different modes, say of different frequency or wavelength, which are very close to each other, not too far from each other, and the other is, say, this one. So in which case the frequency will be high. Suppose this I take for a particular time. This is say this is the time period of 1 second. Okay, and this is also time period of 1 second. So in 1 second only you will see that only one and half, or yeah, one and half part of wave is getting completed for this, and meanwhile in this case the three waves, you can see that there are three complete waves, so the frequency of second is greater than first. Okay, but in our case we have to study a different thing, that is what is the relation between repetition rate and the pulse width, and that too with the number of modes. So number of modes is, say, in this whole mode log laser there are n number of modes. And the second thing, the second factor is TP. The TP is called as the repetition rate. Sorry, the TP is called as the pulse width. And what is the third thing? The third thing is repetition rate. So repetition rate is denoted by T, and I write it as repetition rate. Now, from the module, what we have studied, there are two relations. The first one is with the TP. Say TP, the pulse width for, okay, it will be more clear if we see in this diagram. So in this diagram, you see this portion for which the whole, the intensity is of the laser beam exists. That particular time is the pulse width. So TP is the pulse width, and what relation it has is 2L upon NC. Okay, so TP is simply, in simple words, it is given by 2L upon NC. Now here there are four factors which on which the on which the pulse width varies, and out of that L is the cavity length. So L is the cavity length. The second thing is N. The N is, as I told, number of modes. And the third factor was C. So C, what is it? C is the velocity of light beam. Now, in so as you can see from the relation, the TP, the pulse width, is inverse in relation with the number of modes. Here, what they are trying to ask is, upon increasing the modes log together to produce a pulse laser beam. Therefore, the relation which we got is N is the number of modes is in inverse relation with TP. Therefore, if you increase the number of modes, anyway the pulse width is going to increase, and therefore for this we'll go for decreases, and the second thing decreases is here. So there are two options which where we are able to see that the pulse width has inverse relation with the number of modes. Okay, now the second thing is, what about the T, that is the repetition time. So T is the repetition rate or the repetition time in which the pulse repeats itself. From this whole diagram, it will be more clear. That is, suppose this is the pulse 1, this is the second. This pulse will repeat itself one after the other, one after 2 to 3, in a particular period of time. Say that period of time is 20 nanoseconds. That is denoted by t, and it also has some relation with the length of cavity and the speed of light. For that relation, the that relation is T is equals to 2L upon C. Again, the variables are same as in this equation. L is the length of cavity, C is the velocity of light. Now, coming to the question back on increasing the number of modes. What I have written in this equation, maybe you will get the point, is that the relation of repetition rate with the number of modes, like there is no relation of the repetition rate with the number of modes. Now, however you change the number of modes, the repetition rate is not going to vary, therefore, it remains the same. So, first of all, they have asked us respectively. So, for repetition rate, our answer is unchanged. What is our answer? That is unchanged, or in other words, what they have written remains the same. Now, we had got two options which we had a doubt that they may be correct, and we'll opt for this option which is remains the same and decreases. As they have talked about the respectively thing, the repetition rate is constant, that is denoted by tt, and the pulse width is tp. Now, pulse width, what is the pulse width? It has a unit of, say, any unit of time. It can be femtoseconds, picoseconds, or nanoseconds, or microseconds. It can be of any unit. Now, what I just want to say is, what is the relation of pulse width with the number of modes? This is the relation which we can exploit to get a pulse which is quite narrow. Okay, so suppose you want to get a pulse with you want to get a pulse laser with a range of femtoseconds. So you need to increase the number of modes so that you get the shorter pulse, or your pulse width is shorter. Okay, so here I'll be drawing a diagram which we had studied in the module itself. Suppose you have a laser beam which has, say, 500 modes logged, and the other which has, say, 5 or 50 modes logged. So for the 50 modes logged, you will get something like this. This is something you will get for 50 modes. And the other thing I'm denoting with a dotted line. For a dotted line, you will get, yeah. So for a 500 modes, you will get a more sharp laser, more sharp and very less pulse width. So in all the pulse width, if you take it to be like this, the pulse width for the 500 modes is reduced. Okay, so that is why, in order to get a shorter or the narrower band, you need to increase the number of modes in your setup. Okay, so the first of all, the answer for the question one is, first I'll repeat the question. Upon increasing the modes locked together to produce the pulse laser beam. First of all, mode locking is a technique with which we get a pulse laser. What is a pulse laser? A pulse laser is something which has not a continuous wave, but with the regular time intervals it repeats itself. That is, for a particular range of time, its intensity reaches to maximum and then again turns to zero. So this is a pulse laser beam. Then the third thing is the resultant repetition rate and the pulse width. So there was a relation between the repetition rate and the pulse width. That was that Tp is equals to 2L upon Nc. Here Tp is called as the pulse width, and it is given by the relation 2L upon Nc, where N is the number of modes. Therefore, we can conclude that the pulse width has a negative in relation with the number of modes. The more you increase the number of modes, the reduced will be the pulse width. And therefore, here also we got to know that the more are the number of modes, the lesser will be the pulse width, and therefore In order to get a pulse, a narrow pulse in the range of femtoseconds and picoseconds, you need to increase the number of modes to an extent. Now suppose you want to get something in the range of picoseconds or femtoseconds, you need to have modes which are in the range of 10 to the power 6 to 10 to the power 8. So that is quite a large number. The second thing is repetition rate, which we denoted by a capital T, and capital T has a relation that is 2L upon C. Here there is no existence of number of modes, the n value, which states that the T repetition rate remains unchanged whatever are the number of modes, whether they are 50 or they are 500. It does not change. Okay. With this, if you any of you have any doubts, you can just take your time and ask the doubt, and then we'll proceed to the next question. I'll just wait for a few seconds. Okay, so now we are going up on to the next question. That is, for a pulse laser, the spectrum of whose spontaneous emission is provided above pulse duration is. Okay, so in order to understand this question and from where we can get the relation, here we have kept a diagram that is to calculate the pulse duration. So first of all, suppose you take other wait, we would have one another diagram. Just a second. Yeah. Suppose okay, this picture I'll just copy there. Yeah. Okay. So this is the spontaneous emission band. This is the spontaneous emission band, and the second thing is the half width and half maxima of this is given by the delta lambda. The second thing is this is the stimulated emission band, and the wavelength the at which the maximum intensity is there for the mode log beam is given by the lambda, and the fundamental beam has the lambda naught for the mode log beam, and the second is the lambda for the you can say the fundamental beam which is being used. Okay, so here we could get the first of all the n, the relation between the n number of modes and the 4l delta lambda is given by 4l delta lambda upon lambda naught square. Here l is the again the length of cavity, delta lambda is the value of half width half maximum, or also called as the laser action threshold, and the other the lambda naught square, which is given here. This lambda naught square is the value of the modal wavelength or mode log wavelength. Okay. Also, we are asked to calculate the value of pulse width. For there, we have a deeper or the more illustrated diagram. Yeah. So in this diagram, as we can see, the intensity of there is one more relation of the intensity of the beam with the the modular squared electric field, and that is given by I is equals to n naught, where n are the n square into e naught square. Here e naught is the value of the electric field, and n is the value of the number of modes. Therefore, the more are the number of modes, the greater is the intensity for a constant electric field. So this is the relation given here. First of all, we'll go for the pulse duration. So this is the thing which we talked about, the pulse duration, the time period for which the pulse exists, and the relation for that was Tp is equals to 2L upon Nc. Now, now there are furthermore expression which we can where we can use this value, and using the value of delta omega q, which we got from the q factor value, whose value was given as, and q whose value was given as 2 pi into tau upon t naught, we could deduce a relation which was this, that is lambda naught square upon 2c delta into lambda. Okay, so from here, from the further calculation, where we can relate that equation of this electric field with the further sign equations, and therefore we can conclude that the value of Tp comes to be lambda naught square upon 2c delta lambda. Here delta lambda is the half width, half maximum, c is the velocity of lambda, and lambda naught square. Okay, I think someone is trying. Yeah. So with this, we'll proceed to the third question number three. The question number three is for the TEM XY mode of a laser depicted above. Okay, actually, I think we missed the diagram. So it was something like this, where we had this dark phase, this as the other, and okay, and here they were the four white colored lobes. Okay, and the lobes we can also call them as the nodes. So first of all, I'll just check if we have the, okay, yeah. So for the tem xy, tem stands for transmission. Oh, sorry, tem stands for transverse mode. Okay, so for the transverse mode, when the lasers are when the okay, from this diagram we'll get to know that how these transverse modes are being labeled. So first of all, in this whole figure, you see that there is only a one dark colored, or this is obtained when you have a laser, you just incident on something solid on which it is spot. So on this laser spot, if you get a circular spot which does not have any bright area, which does not have any node, then this type of transverse mode is labeled as 0 0. Why? Because here x and y, in the here x and y, they indicate the number of nodes. Okay, in the x and y, although these x and y, they are not definite, like you cannot say whether this axis is x and this axis is y. It is according to our own preference, whatever we say. The second thing is, as you can see, if you consider x and y, this area, that particular, that is the nodal part, and therefore you get the your spot that is divided into two. Okay, so that you will name as 1 0. And suppose if you get one here and one there, like, okay, you get the two nodes, the one in the x plane and the other in the y plane. Okay, so basically for this you tell that it has one xy mode. And for the other transverse mode, say this, although this is just opposite of this, we do not know, like this one can also be called as 1 0, and this can also be called as 0 1 when we change the axis. So for this you will see that there is one node that is in the one of the planes, so either x or y, you can name it as 0 1. The 1 stands for the number of nodes. And for here, say this is the x axis, and okay, say this is the y axis or the other. You see that 1 2 3 4, here the beam is split, like you get the spot divided into five fractions, and therefore there are 1 2 3 4 nodes. Okay, so for this you will label it as 4 0. And remember, there should be no comma, should be simple xy, and this is the radial node. Say there is a sphere, and the inside part, inside there is a node. Now the diagram which was given there was something like, say that this was the total square pulse, and here you could say square beam, and say here it was like this, and this was also dark appeared. And yeah, so here you could see these four lobes. Okay, or say four nodes which were separated. Yeah, so this was the overall diagram. I think I missed to add that diagram or the picture above. So here you could see that ideally, means if you carefully look at the picture, you will see that this is somewhat similar to the dx square minus y square orbital. And here you see that this is the overall a mode. And if you go on like this, here you will not find, but here you will see that there is one node and going on this axis. Now say this is not straight, unlike these where you could get an axis line like this, but in this case your axis is along this direction. Suppose along this direction and this direction, you get the bright part, and which indicates that there are nodes. We do not get the laser spot on these points 1 2 3 4. So here you can say that the 1 2 that corresponds to the x axis, so there is one node in the x and one other node in the y, and therefore you can say that the value for each is x and y. Now looking at the other options, here I have also added a diagram for the a picture for the transverse modes that we had already discussed in our session. You will see that the first one, 0 0, in this case there is no node, and the node indicates a white spot in the picture. The second one is 1 0. So for the 0 0, we'll get a spot something like this, where there is no bright spot or there is no node. This is the first option, and practically this is not the correct option for our given question. The second one is 0 and 1. For the 0 and 1, as you can see, or 1 or 0, you will get something like this. That is, you will get one continuous line and the two, only two spots. Okay. Whether it is in this orientation or in this orientation, this whole part will be the bright one and these will be the dark ones. Okay. Here also I'm just labeling the dark one with something these lines, and this is the bright spot. Okay, so this bright, they where you will find there is no intensity of light, and therefore these are labeled as 1 0 or 0 1. Vice versa, any way you can take. There is the last, this last option is the only one which goes on with a given figure. That in the given figure, say this is the square shaped um, spot on the paper, whatever. There is the, this is the square shaped laser beam. So in that case, the axis is not along, say, the perpendicular ones which we normally had seen. This is along this and are 90-degree to each other, say here, and therefore the bright spot which we could get, the 2 and 3 and 1 and 4, these corresponds to the one node which is in x plane and the other node which is in the y direction. Okay, so for this is our right answer. Yeah. Okay. So if you have any doubt in this question, you are free to ask, and then we'll proceed on to the other question. Okay. We'll proceed to the fourth question. If n naught is the refractive index of the light of a very low intensity. So first, what is written? Refractive index of light of very low intensity. Then what is the relation between the refractive index n and the intensity of light I? Actually, ideally, what we studied to attempt this question first, we'll just take a quick revision of what refractive index is. So according to the Snell's law, if light passes through one medium, say uh, this is the angle of incidence and this is the angle of, suppose this is a transparent medium, but say this is air and this is water. Now when it passes through this medium, what you will see is, since the density of these two varies, the velocity of light is not the same. When it goes through a medium, something whose refractive index, or say the density, is greater than that of the previous medium, say density of water is greater than density of air, first of all. And therefore we can also say that in terms of refractive in because of this denser medium, the velocity of light, the speed of light in air will be faster than water. Okay, now this difference in velocities causes the beam of light to deflect a bit. Okay, like suppose it does not go straight through this way, but it deflects a bit toward, and here what this straight line indicates, this is the normal. Okay, so this is the normal ray. So when it incidents on any medium and enters through it through a medium, due to the change in density, there is a difference in the intensity. There is a difference in the angle of incidence and therefore an angle of diffraction also. And what is this process called? This process is called as the refraction. So angle of incidence and angle of refraction is not the same. Now, when it passes through a medium compared to air, since air is taken as the standard, how much the refraction is occurring, or how much the light beam has a bent or change in angle, is given by the Snell's law, and that is given by sine sine of angle of incidence of upon sine of angle of refraction, and its value is equal to a constant, and that constant is equal to the is given by the refractive index. In simpler words, if I want to say the compared to the incidence and refraction, say if the angle of incidence is say 50 degree, the angle of refraction will be less for a denser medium. That is, when it moves from a rarer to a denser medium, the light beam, it shifts towards the normal, and vice versa. Now if the light beam on opposite is going from water to air, it will move away from the normal. Okay, so these are the simple terms which we have studied long back. Now I'll come to this. If n naught is the index is the refractive index of light, okay, of very low intensity. Now, then the relationship between the refractive index n and the intensity of light is, okay, so n is the final refractive index, okay, and the second thing is n naught is the refractive index of light. Now there is a law, that is there is an effect, that is the Kerr effect. First of all, what does this Kerr effect say? Kerr effect says that if the laser beam passes through a medium with a particular which has a particular refractive index, then the intensity, then the then the refractive index of that particular light beam will change. Okay, and that is the intensity dependent refractive index, which is given by this equation, where n is the change which is what in the refractive index, and n naught is is the refractive index of the light beam, and I is the intensity of the light beam. Okay, and the other thing is, see, suppose I call this laser beam to be a Gaussian one, that is, its intensity is given as first it increases to maximum and then reaches to zero. Okay, so how on a plane it can be drawn from the center? As you go on increasing the radius, the intensity goes on decreasing. As you can see, intensity has a negative relation with the r. R is the radius of this sphere. Okay, now as this intense beam passes through any other medium of some refractive index, okay, so what will happen is, since it has more refractive index and this beam has the maximum intensity here, so the final refractive index, it depends on n naught, which is a constant value, and that too I. Now intensity, talking about the intensity in the center is greater than compared to the intensity on these two. Okay, and therefore the resultant refractive index value for this will be greater than compared to the one in the corners. Due to this change in the refractive index, we get a variable density. Therefore, the NZ in this particular direction for this active medium will form like this shape, which concludes that the refractive index on the corners is less and the refractive index in the center is more. Okay, now we'll come to our question. uh, what our question says is, the if n naught is the refractive index of a very low intensity beam, then the relationship between the refractive index n and the intensity of light is, okay, so however the intensity is low, but although this effect is only applicable for the light beams which are of comparatively high intensity. Okay, so therefore we come to that this is the relation which relates the final refractive index and the refractive index of the beam of light and the intensity of light. Okay, so if you want to find the resultant refractive index, you should follow this equation and you will get a value. Here n naught is the refractive index of the incident light, n2 is some constant multiplied by I. Okay, the I is the intensity of light. Once again, I like to try to revise that. Suppose what here, simply the relationship between the refractive index of light and the final refractive index and intensity is being asked. So there is a direct relation, that is n is equals to n naught plus n2 into I. Here n2, say, see, since refractive index has no unit, it is unitless or say dimensionless, and n naught also does not have any unit. If you talk about intensity, it has some unit, and therefore the n2 has a unit, that is inverse of intensity. Okay, and therefore these cancel out each other and you will get the resultant, that is unitless. And the other thing which we discussed in this question is simply what is the refractive index. So each medium has a particular refractive index which we can calculate by the angle of incidence and refraction. Also, we also got to know that if the light passes from a rarer medium to a denser medium, or vice versa from a denser medium to rarer medium, there is a property that is called the refraction occurs. That is, there is change in the angle. This change in angle also brings out the change in the velocity of light. Suppose it passes from a rarer medium to a denser medium, there will also be decrease in the speed of light. Not only there will be change in the angle of incidence and refraction only, there will also be change in the speed of light. Okay, when it passes through a denser medium, the speed of light reduces. And also this application will study in the further questions what is the relation and how can that relation be used in the other techniques. Okay, so answer for this question is the first one. This is the answer, n is equals to n naught plus n2 into I. Now if you have any doubt in this question, we'll wait for a time and then we'll go on to the next question. Yeah. So with this, we go to the question number 5. In the titanium sapphire laser, the titanium sapphire laser is inherently mode locked by. Okay. So as I told you, how we are going to use this application of uh, Kerr effect, and therefore try to get the mode logging of laser with by using Kerr effect itself. Okay. Yeah. So first of all, what is a titanium sapphire laser? Titanium doped with sapphire. Okay, in a particular ratio. And what is sapphire? Sapphire is something aluminium oxide. Okay, with titanium. This forms the titanium sapphire laser. Actually, in the previous week, we had also discussed what is the wavelength of titanium sapphire laser. Okay, so first of all, yeah, water titanium sapphire laser, how is it mode locked? So, first option is the acousto-optic modulator, electro-optic modulator, De Sears mode locking, or Kerr lens mode locking. The first of all, let me tell you the acousto-optic modulator and electro-optic modulator. These are some devices which are used externally for the mode locking, and the process in which mode locking is done using some device that is called as the active mode locking. Okay, so first of all, what we'll go on, the for the later two acousto-optic and the electro-optic modulator we'll be studying later, and along with the device years mode locking. The first is the Kerr lens mode locking, which using which only we'll get to know our answer. So, what is the Kerr effect? Now, first of all, say we have a Gaussian laser beam. What is a Gaussian laser beam in 2D? If I want to draw it, is like that. Although it may not be proper one. Yeah, so I'll draw it along. Yeah. Suppose I draw it along this, along a plane. So what I would like to, how I will show it is, its intensity is like this, increases and then decreases to zero. Okay, so this Gaussian laser beam, if I want to draw its plot on a paper, it will be like these are the concentric circles, and here it has the maximum intensity. And from the figure you see, this is the part which is the maximum intensity. Got it? The other thing is, now as this beam passes through the medium, okay, or if you want to say this is the refractive index along the x and y plane, what you see is the, say, uh, when it passes through a medium, what happens is, it has the maximum refractive index, and further refractive index goes, sorry, it has the maximum intensity and this has the least intensity. Say I draw 2 points, this is the n0 and this is the n4. Now compared to n0 and n4, okay, here we got to know actually, okay, we'll write it as n1 and n2. The total n is equals to n1 plus n2 into I. Here n1 is the refractive index of the light beam, and the further the total refractive index that varies upon the intensity. Now what I would like to say is I of n naught at the point n naught is greater than intensity at point n4, and therefore the resultant n for 0 is greater than refractive index for n is equals to 4, and therefore within the same we'll get different values of refractive index. At this point the the refractive index at n0 will be lesser than the at n0 will be greater than n refractive index at n is equals to zero point 0.4. So here I label it as n4 and say this as n0. Now this whole thing looks quite similar to what we call it as the convex lens. Suppose this is your convex lens, or in for a better drawing I'll erase it. Yeah. Okay. Suppose this is your convex lens. Yeah. So this is your convex lens. This is your convex lens. If you draw, this is the optical axis. So you will see this has more refractive index and this portion has less refractive index. Because of this less refractive index and more refractive index, See, as the refractive index increases, say the light beam is coming straight. Okay, so light beam when it comes straight from here compared to this and this point has lesser refractive index, so it will deflect less. Say only this much it has deflected, but at this point the refractive index is more, so it goes straight and then again it moves. Say this much, the third beam which lies here, the third point which I take here, the light beam passing through this point, it will concentrate more. So in this way you will see that the light beam, suppose they are coming parallel to each other, because of the variation in the refractive index, change in the density, they get converged on a single point. Okay, and therefore we get a highly focused beam. Now, say I'm talking about this pulse light, okay, and I'll draw this diagram more in a more fair manner. So what basically Kerr effect is, since the if you talk about the even the pulse laser beam, which has a high quite a high intensity, when it passes through a medium, due to the like because of this Gaussian laser beam, it has uh, it has a variation in intensity. Say from this point to this point, this has a higher intensity than this. What happens to these lower intensity points is then studied. Because of this lower intensity, the resultant refractive index is less compared to the one that is at this point. Say this is N4 and this is N0. So, anyway, the resulting refractive index at N0 will be greater than N4. Because of this difference in refractive index, this whole thing behaves like a lens. This behaves like a convex lens. At this point, the light beams which are say parallel to the lens, because of the medium, because of the change in density, at this point this diverges or shifts the least, this shifts the most, then further because of this all these light beams they converge at a point. The reason for this is the lesser is the refractive index, the least it will be diverged. But on increasing the point, say on moving downwards, you will see that the index is increasing, and therefore the diffraction, or sorry, the refraction from its original angle of incidence will be more, and finally these all will be focused at the point, say this one. Okay, so this is how this Kerr effect works, and actually this is a property of nonlinear optical materials. Here also we have given one relation, that is f for the focal length. Focal length of the Kerr lens which is made depends on the w square 4n2 I naught into L, where L is again the length of cavity, I naught is the intensity of the incident beam, n2 is the refractive index. Sorry, n2 has inverse relation with the intensity, it is some other variable, and w is the width. Okay, and also there is one more important point. Suppose our beam is not, that is a weak beam, or it is a not a more focus. So what happens, it somewhere the value of I is less and n is less, so the Kerr effect will not be more pronounced for the, or the beam will not be that much focused. Why? Because since the intensity is less, the further the whole this nz is reduced and the beam will not be able to focus. So for a so this Kerr effect we will not be able to see for a continuous wave light, or you can say a pulse light with of a low intensity will only see this Kerr lensing for the pulse light of higher intensity and not for a lower intensity. Got it? So here we come to the answer. The titanium sapphire laser is inherently mode locked by. Now here I was talking about the refractive index of the light beam. Then it passes through a medium that has certain refractive index, and how its refractive index changes, and how the medium works as the curl lens itself. Now here if you talk about the titanium sapphire laser, suppose the active medium through which it is passing, it is simply the titanium sapphire laser. Why? Because suppose this is the laser beam, we are from the source, it passes through this active medium A, and then it again moves back. There is a reflecting mirror here which reflects the light back again in this medium and then passes through. What we got to know from this figure is, because of this continuous to and fro movement, the waves itself in this are mode locked. And how this mode locking is done, since the mode logging is done means the only the intense part of the beam, it is more focused, and therefore you will the continuous wave part will be eliminated, and the intense beam part will be the one you will get, and therefore you can get the pulsed beam. So in the titanium sapphire laser, this curl lens mode locking is the thing that works and is responsible for the inherent mode locking thing. Okay. uh, uh, if you have any doubt in this question, we can discuss, and then we'll proceed to the other question. And one more point to discuss here is that if n naught is the refractive index, then this curl lensing will not be observed for our case, because here they are talking about the very low intensity beam of light. And therefore this equation, although this equation will be followed, but since the value of I is very low, will not get that curl lensing thing which we have studied. Although it will follow the same equation, n is equals to n naught plus n2 into I. Here I is the intensity, n2 is the inverse of the intensity, n naught is the refractive index of the light. Now we'll go to the question number 5. Okay, yeah, and the titanium sapphire laser is mode locked inherently by curl lens mode locking. The curl lens mode locking is based on this curl effect, and in this case what happens is the in the specific number of modes gets restricted and are separated because of this curve effect of the refractive medium itself. The weak beam that is not focused, and we do not get anything, but only the focused beam or the intense beam of part we get in the as the resultant beam. Now, the coming to question number 6, the prism pair inside the titanium sapphire laser does what? Adds chirp of the pulse, decreases chirp of the pulse, decreases the temporal width of the pulse, or increases the spectral width of the pulse. Okay, so along with this curl lensing, there was a drawback which we had studied, that was the chirping which would occur. What this chirping is, suppose this is the pulse of light which is passing. Say it is in the form of this, and it has a bandwidth spectral width of this much, and these are the different wavelength of light. When it passes through a medium, say this much, it will just get dispersed. It will undergo the GVD, group velocity dispersion. Okay, and how it can be, say the different colors are separated, and what are this separation, because what is this separation called? This is called the chromatic aberration. What happens in this case? How are these separated? So these are separated by C. If you see this whole system, the refractive index of this is less and this is more. Now suppose the light is passing through this medium, say that there is change in the effect. Again, if it passes through a medium, because of its refractive index, the light beam which has different parts in it, say this much, one, two, three, four, which have different velocity and different frequencies, it is split into its components. The phenomenon of dispersion occurs, because of which there comes a broadening, like you get each of the bandwidths, they are separated. Okay, so you will get a broad band. Now what you want to do is, you cannot uh, like, this is not the right choice, you cannot go on with this, you need something which is better than this. You need something which can compensate for this dispersion, and therefore this whole chirping can be reduced. In this chirped input pulse, you will see in this diagram, see the frequency, some has higher frequency, the other has low frequency, and therefore they are separated from each other and you get a broadband. Suppose I say you that this is something blue and this is something red. As you can say, the frequency of B, say blue, is greater than that of red. Now what I'll do is, although if you ask them to pass through a straight path, B will reach faster than R. Okay, so sorry, R, like, this is R, so B will reach faster than R, and which is would be the reason for this aberration or dispersion which is caused. Now if you want these to be traveling at the same, or these to be coming or focused at the point at the same time, and therefore reduce the chirping, what you need to do is, the one which goes on with a faster speed, you need to go on, you need to reduce its speed, or instead of reducing speed, you can ask it to go on through a longer path. Okay, so for a longer path, the beam, the chirped pulse which comes to us, that is passed through a pair of prisms. The pair of prisms, what do they do? Say these are the pair one, two, three, four. There are two pairs of prism. What do they do? When you pass this chopped pulse through that, obviously the light beam will get dispersed or get refracted. When it gets refracted, it breaks into its components. Say this is blue and this is the red. Now see, since it travels a shorter distance, or since its velocity is high, since its velocity is, say its velocity is slower and its velocity is higher, so what you want to do is, this blue portion, you will ask it to run through a longer path, because it travels through a longer path and this travels through a shorter path. Consequently, both will reach at the same time to the final, and therefore in this way, you will get a sharp chirp free pulse, that is at as the output. And actually this thing you can, when you see in the instrument, there is some setup where using the screws you can just adjust their distance, and as this distance changes, you can adjust the output pulse which comes out. Like if there any is any disturbance and still you see any phase difference or a chirped input pulse, you can change the position of these two prism and finally get an output which is chirp free. Okay, so what is the purpose of this prism pair? What the uh, In the titanium sapphire laser, actually, despite the curl lensing, when you get a mode lock laser beam, then also there are certain drawbacks. The first drawback is the chirping effect. What is the chirping effect? Due to this change in the velocity, there comes a broadband, and in this broadband you see there are variety of velocities of light which are separated from each other, and we get a broadband, and this is also called as the group velocity dispersion. In order to reduce this dispersion, what we use is this pair of prisms. The pair of prisms, when managed in this way that they are perpendicular to each other, what you see is they are managed at a certain angle that when the light beam passes through them, they are not like they are not, they allow the light to pass at a certain angle, that the beam, the part of the light beam which has more intensity, that goes on through a long sorry, the part of the light beam which has a greater velocity is allowed to pass through a longer path, and the part of the light beam which has a lower velocity is allowed to pass through a shorter path. And when they reach through the final destination, the final point, it so happens that they meet each other. Why? Because the time taken by each is more, and sorry, why? Because the although the velocity is different, but the distance traveled by each is different, and therefore the time is covered up. Now, uh, through this explanation, I suppose that you may get the correct answer. Although I want to say that there is a special thing about this, like this question is one of the MSQs where you can get more than one option for one right option for the question. So, for this question, the prism pair inside the titanium sapphire laser, what does it do? It adds chirp to the single signal. It adds chirp to the pulse. First of all, this cannot be the right option, anyways, because we few seconds back we had discussed that this is prism pair can reduce the chirp. Okay, the of the pulse. So, first option. So first option is wrong. The second is decrease the chirp of the pulse. Okay, yes, this option is correct. The third option, now we have to consider the other options as well. Decreases temporal width of the pulse. And the third is increases the spectral width of the pulse. First thing I want to say is that what is the temporal width? The temporal width is something which is related to the lifetime or the time period for which the pulse exists. If you want to, if something is not clear to you, just look at the diagram. The in this picture, what the figure they have given of the chub pulse is, the chub pulse is something which is very broad, and the output which we get when the light passes through this whole prism system is like it is in the form of compressed output pulse. Therefore, from this picture, thus we can conclude that the temporal width of the resultant wave is quite reduced compared to the input wave, and therefore it also helps to decrease the temporal width. One of the reasons for this is, see, all the beam is quite focused. Okay, and with respect to intensity, the pulse, its value turned to be shorter. Why? Because all these now have compensated, and within short time you will get a highly intense pulse. The third thing is increases the spectral width. What is spectral width? Is something related to the intensity. Okay, and if you talk about the intensity, I what I think is that when it passes through this certain long sphere, there is nothing which can change the intensity of the light. In fact, it goes out quite strongly focused, although the width does not increase. Okay, so spectral width does not increase, although the temporal width of this input pulse decreases, and also the chirping in the pulse also reduces. Okay, now if you have any doubt in this question, we can wait for some time, and then we'll proceed to the other question. For our question number 7, the saturable absorbers lead to passive mode locking by water saturable absorbers. So there are few new terms in this question: saturable absorbers and passive mode locking. What is this saturable absorption? Something that absorbs the intensity of light to more than one, that is called as the saturable absorber. Okay, now a saturable absorber, for this we had studied in the module that certain DOD-CI laser, and the second is rhodamine 6. These are some dye lasers. Dye lasers means what? It is not something solid. It is in the solution state. The dye laser, they act as the saturable absorbers. Saturable absorbers, what do they do? This function we are going to study like here only. And the passive, so something which uses, see, there are two terms. First is the active mode locking and the second one is the passive mode locking. So what is in the active mode locking? Active mode locking, if it uses some instrument. Okay, if, yeah, if you it uses some device for for mode locking the pulse, then it is called as the active mode locking. The second thing is, if it uses some chemical, then it is called as the passive mode locking case. What happens in this saturable absorber is, say, the light beam for any from any pulsed source, after continuous refraction, it passes through this saturable absorber. Say its name is rhodamine absorber. So what happens is, this saturable absorber, say, in terms of energy levels, it has some energy levels n1, which is the ground state, and n2, which is the excited state. Now, if the incident light beam is of sufficient low intensity, what happens, this is unable to excite, or it excites some of the population from n1 to n2. Okay, so in this case, absorption will occur. What will occur? Absorption will occur. Only some population of n1 will be able to reach to n2, and therefore the rest of the population still resides in n1, but the relation that continues to exist is n1 is greater than n2. The Now this is also applicable for the continuous wave. If the continuous wave is of sufficiently low intensity, the same thing happens, although if the continuous wave may excite the population to some extent, but then again the relation of almost n1 is almost equal to n2 comes, but again it does not happen, so that the population of n2 will be greater than n1. The third one is the pulse light. So far we know that the pulse light is quite intense compared to the continuous wave light. Okay, so this pulse light happens like pulse light is the only one which causes a situation where n2 will be greater than n1, and as soon as n2 will be greater than n1, emission can occur. Okay, so this is the thing which it can do. This is the saturable absorber, which does the following function. Okay, at this point when emission occurs, n2 will be greater than n1. What we want to conclude is, what does this saturable absorber does by doing these things? The first thing it does is, if the intensity of light is sufficiently low, so that it is in the range, like it can only excite the n1 population to some extent, but not greater than but in never ever it will happen that the population of n2 will be greater than n1. It so happens that most of the light beams, most of the intensity of light is absorbed. That is the process of absorption which we discuss. Now suppose, increasing the intensity, we come to a point where n1 is greater than n1 is equal to n2. That process, at that point, bleaching will occur. Okay, the third thing is when emission will occur, when you have sufficiently intense beam, so that the n2 will be greater than n1, and further the emission will occur or the transmission will occur. Okay, so basically this saturable absorber does that. The low intensity beam of light, it absorbs low intensity light beam, and transmits only the high intensity light beam. Got it? Now, saturable absorbers, what is this passive mode locking? Now, since it absorbs the low intensity light, it transmits only the high intensity light. Suppose a collection of this, say this is going through this saturable absorber. Okay, when you when you go on to the resultant beam, what you will get is only this point. Okay, you won't get these and these because these are absorbed by the saturable absorbers, and that is why what you get is the transmitted pulse beam, which has quite a high intensity, and rest of the light beam, the low intensity part, is already absorbed by it. Okay, so passive mode locking, or you can say the mode locking, is achieved in this case by absorbing the CW and transmitting the pulse light. This is our first option. The second is absorbing the pulse and transmitting the CW light. The third option is absorbing both CW and pulse light equally. The fourth is a nonlinear absorption. So, absorbing CW and transmitting pulse light may be the right answer for this question. The reason for this is if it does not absorb the pulse and transmit it. Why? Because the pulse light is quite intense that it can be transmitted by the saturable absorber. The second is absorbing both CW and pulse light equally. So yeah, maybe it absorbs both, but it transmits most of the pulse light. So this is also not the option. The third option is a non-linear absorption process. So this process we'll study later. This is not related to it. But from the whole solution to this question, we came to a conclusion that by absorbing the continuous wave part and transmitting the pulse light, we could get something which is the passive mode locking. Therefore, the pulse will be sharp mode locked with a small uh, time width. Okay. So answer for this is absorbing the continuous wave and transmitting the pulse light. If any one of you have any doubt in this question, I'll wait for a time of 1 minute and then you can ask your doubts. We'll proceed to the next question. Okay, with this, we'll move on to the next question. Active mode locking can be achieved by. Okay, so first of all, we'll note what is the difference. First is active mode locking, second is passive mode locking. Okay, what is active mode locking? Active mode locking is something which uses device to mode lock the laser, while passive mode locking is something which uses an element or a medium to Mode lock the laser. Got it? Now, active mode locking can be achieved by acousto-optic modulator, by electro-optic modulator, in Ramatnath regime by saturable absorber. Actually, the points here, this is also a multiple selective question. This is not uh, this question does not have a single option correct. First of all, for your explanation, I have kept the diagram of acousto-optic modulator. So, what is this AOM? That AOM is also called the acousto-optic modulator. How does it work? There is a De Beziers effect. See, there is a difference between the light and sound. Okay, the first thing is the light beam, that is a transverse wave, and the sound, that is a longitudinal wave. Okay, now see, when the light beam of say frequency, here I can say it is omega, uh, here we pass it through a medium, say this one, then again there is a sound frequency. Why? Because the acoustic, what does the word acoustic suggest? Acoustic suggests something related to sound. Okay, so here are there here is a transducer. Okay, the source of sound frequency. So here is some transducer, and here is some, you can say, a quartz plate. Okay, so here is quartz which can block the uh, propagation further. So when the sound waves from the transducer, they reach to this medium, and for this medium, say this has something, a medium which has a definite density also, and also a particular refractive index. What happens is, see, the sound wave, it how does it propagate? It propagates by compression and relaxation. Okay, so compression and relaxation, they occur simultaneously in the medium because of the propagation of sound waves. When the compression occurs, say the waves are quite closer to each other. when the rare when they are rarefied, they are quite far from each other. Simultaneously, again it happens, they are close to each other, and again they are rarefied from each other. This is the thing that happens. Now, that is quite a sense that when they come closer to each other, the density is more than the density when they are rarefied. Okay, so in this case density is more, in this case density is less. When the density varies like this, we can say that each the part which is gray has a higher density, and part which is white has a lower density. When it passes through a medium which has a variable density at regular intervals, we can say that it is similar to something which is like slits. Like when the light beam passes through slits, what happens? When the light beam passes through slits, because through the denser medium it is quite difficult for, or it passes through a lower velocity, from the other it passes through a high velocity, the conclusion it is, it gets diffracted. What happens? It gets diffracted. Because of this diffraction beam, what you get, the concluding light waves, they are in the same phase, they are not in the different phase, they come to be in the same phase. And through this only you will get that the light beam, is which you will get, it is phase modulated. Okay, they are in at a frequency, say this one, these are the phase modulated, they have the same phase. Okay, now through this only you are able to separate something that is the intense light beam and something that is continuous. Okay, so with this acousto-optic modulator, basically what we are trying to do is we are trying to modulate the light or mode lock the light. So this is one of the methods of mode locking, and that is a part of the active mode locking case, where we use a device, and that device is used, and that device, using the sound waves only, it is able to modulate the light. Now the second condition for this to happen is, for the acousto-optic modulator, the L, which is the length of the cavity, it should be lesser than the value of lambda square upon 2 pi lambda. Here lambda is the velocity wavelength of sound, and this lambda is the wavelength of light. Okay, so basically something that is if this length is lesser than the this particular relation, if it follows this relation, then only you will get the this de Beziers effect, and then only you will get the active mode locking. So therefore, actually, this will be discussed in the further modules. But the answer to this question will be by acousto-optic modulator, by electro-optic modulator, or if the thing is in lies, if the length of the medium is in the Raman-Nath regime, or it follows the following rule, the particular rule: L is lesser than lambda square upon 2 pi lambda, where lambda above, which is the square, is the velocity wavelength of sound, and the one in the denominator is wavelength of light. Therefore the active mode locking can be achieved by acousto-optic modulator. Acousto-optic modulators are those, see, this is the standing waves, they're which are like whose amplitudes do not whose only amplitudes vary, but the position of nodes ideally they do not vary. The incident radiation frequency when it passes through a medium of a refractive index n1, whose refractive index is also changing with time, then you will get a phase modulated light whose frequency, or which are in the same phase or not in the different phase. And this is also called as the de Beziers effect, where you can get a phase modulated light when you apply the light beam and the sound beam perpendicular to each other at a particular wavelength or frequency. If you have any doubt in this question, then we can discuss, and further we can proceed to the other question. Yeah, okay. So without much delay, we'll be going on to the next question. That is question number 9. Usually, mode locking lasers produce pulsed light with the temporal width off. Okay. So as we had discussed, see, in the first question I had discussed with you, that, see, suppose this is the, yeah, suppose this is the pulse light. Okay, this is the pulse laser, and the second thing is, say, yeah, okay. So maybe, okay, just a second. Yeah, this one. See, here we could see that what are the mode lock laser? Mode locking of laser is something that is used to produce a pulse laser. Okay. Now, if you want to get the this is this mode locking this mode locking process in the laser is the only thing which we used to get, yeah, with the help of mode locking, what we are able to get is, we are able to get something like this. Like the output, which we get, its intensity is quite high, and second thing, it is shorter. Okay, and how we can get through the relation is n is equals to, yeah, n is equals to 4l delta lambda upon lambda naught. 4l delta lambda upon lambda naught. Okay, now one more thing which we wanted to say is, see, say this is the time period, so we had also studied the relation 2l by c, and tp is equals to 2l upon nc. See, this TP is something, say this one is the value, this is TP. So TP is something which is related to N, which is the number of modes. Okay. And the number of modes in the laser, if you increase the number of modes, you will get the value of TP less. And this TP is something which is related to the temporal width. Which is the temporal width? Okay. So temporal width means something related to time. Therefore, for this pulse only, we can get the width as much less as possible by increasing the modes. Okay, so by increasing the modes, what you can get? By increasing the number of modes, you can get the decrease in the temporal width. Okay, so instead of this broad band, what you will get is something which is quite sharp. Okay, quite sharp, although it will have some low values, but this depends on the value of n. If you take a very high value of n, you may also get something which is very sharp, which is not very much broadened. Particularly on the application part, mode locking is only used in laser to get a pulse width which is in the order of femtoseconds and picoseconds. Okay, not in the range of nanoseconds and microseconds. Femtosecond is something of the order 10 to the power minus 15 seconds, and picosecond is something of the order 10 to the power minus 12 seconds. For getting certain short pulse of light, you need to do this mode locking procedure. Once you do this, you can get extremely short pulses which can be even highly intense. Okay, so with this, we come to like for this week we have ended the question, but I have also kept some questions which will be a short revision of the previous modules, so as we can like we can use our time to discuss those questions as well. So the first question will be, first, what is the purpose of a neutral density filter? So, what is the purpose of a neutral density filter? If you remember, this thing we had discussed in the earlier experiment setup where we could get the ultrafast lasers. So, the neutral density filters, what they used to do is, if you have a laser source, say this one, if you pass it through a reflector, this say M mirror, and then you pass it through a neutral density filter, that I'll denote by NDF. Passing through this neutral density filter, initially if the intensity of the beam say higher I, it would reduce to smaller value. And the reason for this is when this light beam is allowed to focus on the sample, if there is no neutral density filter on the way, the intensity is quite high. This high intensity beam of light causes the sample to be degraded. So in order to avoid this, we use this neutral density filter. So what is the purpose of neutral density filter? Answer to this question is reduce the intensity of incident light on the sample. Okay. Related to this, there is one more question, that is second, which I'll write here. Suppose there is a short pass filter which allows lambda b and trans reflects. This allows means actually transmits, which transmits lambda b. Okay, I'll write it more clearly, lambda b, and reflects lambda a. Full stop. What is the relation between lambda a and lambda b? Okay. Does anyone of you know the answer for this question? See, answer for this will be, as the name suggests, short pass filter. Okay, short pass filter. What does this short pass filter do? Short pass filter allows or transmits shorter wavelength of light. Okay, and transmits longer wavelength of light. Now suppose there are two wavelength of light lambda A and lambda B. This is say a short pass filter. It has allowed, which had lambda A plus lambda B. It had allowed lambda A and it had reflected lambda B. Or I think in the question it allows lambda b, or transmit allows, yeah, it allows lambda b, so we'll take this to be b and this to be a. So then in case, since the property of a short pass filter is to allow the shorter wavelength of light and do not allow the longer wavelength of light, we can conclude from the relation that first of all lambda a is not equal to lambda b, that is the two wavelength are not same, because otherwise if they would be same, both of them could have passed through this filter. The second thing is Since the B is able to pass, lambda B is shorter than lambda A. Therefore, wavelength A is longer than wavelength B. Got it? So this is the thing. Okay. Now we come on to the question number 3, which we had selected. Basically, from the above two questions, we got to know that filters play a major role when you design any instrument. So filters are something which filter out some the unwanted rays, light beam, which you do not want in your way, and which would again give you wrong readings related to your sample because they are somehow not related to the purpose which we want to fulfill. So, if you have a collection of two beams, say lambda and lambda b, you want to filter out any one of those, you can use something that is long pass filter or short pass filter. The second thing is, if you want to decrease the intensity of the light beam that must be incident on your sample, then you need to use a neutral density filter which does not filter according to the wavelength difference, but it filters or you can say it do not does not allow very high intensity of light to pass. It reduces or cuts off the intensity of light beam. Okay. Now there is one such another question which was related to the intensity or the you can say up conversion process. So here there I have given you the question is a fluorescence decay fit is a fluorescence decay fit is a by exponential function of two components, say A and B, which one of the two contributes more. First of all, for the fluorescence decay, say in a medium, there are two components A and B which emit fluorescence. Okay, so the total intensity which we want to get or the intensity of the fluorescence will depend on the I naught, which is the intensity of the incident light, summation of AI e to the power minus t by tau. Got it? Now, going on with this relation, intensity at any point of time depends on the amplitude, time period, and lifetime. Okay. So, suppose I am given that the value of A and B. Okay, for component A, the value of amplitude. Okay, I'll write this on the next page. Say this is component A and this is component B. First of all, the value of amplitude and lifetime. Amplitude and lifetime. These two are for B, these two are for A. Suppose the amplitude of A is zero point 0.5 and the value of lifetime is zero point 0.4. The value of amplitude is zero point 0.6 and lifetime is zero point 0.3. If I want to calculate the total intensity or the relative intensity, So for the A component, IT, or you can say IA, will depend on AI into tau I. So for that, you keeping the other things constant. Since the other things are constant, you will just find the product of amplitude and the time lifetime. So amplitude is zero point 0.5, lifetime is zero point 0.4, and you will get what is 0.20. Okay. And the second thing is, if you want to calculate IB AI into tau I, it will be equal to zero point 0.6 into zero point 0.3, as we did same in the previously. It will come to be 0.18. Okay. Now let's see back to what the question we were asked. The fluorescence decay, if it is a bi-exponential function of two components A and B, which one contributes more to the total intensity? So if we talk about the total intensity, where IT will again be the sum of A and B. So there we can see that, keeping the other things since they are constant in each of them, the IA part will be greater than IB, since what we have calculated from, and thus the uh, greater contribution will be from the A component. Okay, greater contribution from A component. Yeah. So here will be greater contribution from the A component, and therefore we can see that from the question we'll get our answer that A has a greater contribution than B. Okay. Now the if I say that there are three components, or say if each one has the lifetime of 0.04, 0.4, and 0.4 and 0.4, then only the amplitude will be the something that will be varying. Okay, so amplitude will be something that will be varying. Now with this I'll go to the next question. Sorry. Okay. So with this, we'll go on to the next question. In this question, say this is something related to the previous uh, week's module, which was the question is, which number is this? This is question number 4. Question number 4 says that for an amplified laser, power is equals to 1 watt, repetition rate is equals to 1 kilohertz. Here I'll do it to 800 hertz. pulse duration is equals to 100 femtoseconds and the fundamental wavelength of light be 800 nanometer. What is the first? There are three things which I like we calculate. Energy per pulse. Okay. So see, the power of laser which we were given is power of laser is equals to 1 watt. Okay. And the repetition rate is equals to 800 second inverse. And what is this? 1 joule per second. Okay. So in 1 second, the total power is 1 joule. Okay. And the repetition rate is uh, 800 pulses per second. What I want to find is energy for one pulse. Okay. Now in 1 second, say it is the energy is 1 watt, say 1 joule. Okay. Second inverse per second. And how many are the number of pulses in that? 800 pulse per second. Therefore, total will be 1 upon 800. Okay. So it will come somewhat to be, it will come somewhat to be 1.25 into 10 to the power minus 3. And what will be the unit? Joule per pulse. So for single pulse, what is the power? That is for single pulse, what is the energy it has? That is 1.25 into 10 to the power minus 3 pulse. Okay. Now the second thing, if I give ask you to calculate, that is the number of photons per pulse. What do I want you to calculate? Number of photons per pulse. Okay. Now suppose there is, let's consider a single photon which has a wavelength lambda which is of 800 nanometer, right? In the last question it is given 800 nanometer. Now what will be the energy of one photon? So totally say each pulse has n photons. Each pulse has n photons. Okay. Therefore, total energy will be the n number of photons multiplied by the energy of one photon. So energy of one photon multiplied by n is equals to energy of one pulse. That is it. So energy of one pulse we got. Energy of one photon we can calculate. Energy of one photon will be hc by lambda. Therefore, it will be 6.626 into 10 to the power minus 34 into 3 into 10 to the power 8. Now, what I am using the units, it is joule second, it is meter per second. Okay. And what is the wavelength of this? This is, 800 into 10 to the power minus 9, that is in meters. So, meter to meter will be cancelled, second inverse to second will be cancelled. Now we are going to solve what is the total answer for this. It will be 6.626 into say 3, 19.878 divided by 800. Okay. So it will be Wait, actually it will take, like, we have to correct the power also. 10 to the power minus 34 plus 8 plus 9, and 6.626 into 319.878 divided by 800 comes to be 0.024. Now correcting all the decimals, we'll get that 0.024 into 10 to the power c minus 34 plus 17, it comes to be minus 17. Okay. And yeah, energy per pulse, yeah, it comes to be 0.024 into 10 to the power minus 17. And the unit is joules. Okay. Now here we had one relation, and that relation is for getting to be more clear. See. Yeah. So here n is the number of photons is equals to energy of one pulse upon energy of one photon. That's it. Energy of pulse we got to know is 1.25 into 10 to the power minus 3 joule. And what we got to know from the calculation of energy of one photon, energy of one photon is 0.024 into 10 to the power minus 17 joules. Joule to joule is cancelled, and now we are going to correct this. 1.25 into 10 to the power minus 3, and see, here I am writing 2.4 into 10 to the power minus 19. When it goes up, it comes to be 1.25 upon 2.4 into 10 to the power minus 3 plus 19 is equals to 10 to the power 16, and into 1.25 upon 2.4. So it comes to be 0.52, and since this is a large number, I'm going to write this as 5.2 into 10 to the power 15 photons. So this is quite a large number. Basically, what we want to conclude, this is simply a revision of the last question. For an amplified laser, if the power is 1 watt, if the repetition rate is 800 hertz, if the pulse duration is 100 femtoseconds, and the wavelength is 800 nanometer, we are asked to find two answers, that is the energy per pulse and the number of photons per pulse. So energy per pulse also we could calculate by the simple relation, and using the values which are given to us, energy per pulse, and the second is for first is the second is number of photons per pulse. Okay. Now again, going back, see, we are going to discuss one more question which is also related to something. Yeah. Okay. So suppose in a the question is, In a TCS-PC experiment carried out with a TAC range of 60 nanoseconds, the MCA gain, sorry, the the temporal resolution is if the MCA gain is 6,000 channels. Suppose this is the question. This is the question number 5 in a TCS-PC experiment. In a TCS-PC experiment, say the TAC range is of 60 nanoseconds and the multi-channel analyzer has how many channels? Multi-channel analyzer has 6,000 channels. Then the resolution is. Now see the tag resolution in picosecond per channel is. See, first of all, to get that, as you can see from the unit, 60 nanoseconds is given to us. So we'll convert it to picoseconds. So 1 nanosecond is equal to 10 to the power minus 9 seconds, and 1 picosecond is equal to 10 to the power minus 12 seconds. Therefore, we'll multiply by 10 to the power 3, and it comes to be 60 into 10 to the power 3, or it can be 66 into 10 to the power 4 picoseconds. And therefore, the temporal resolution will be 6 into 10 to the power 4 picosecond. And what are the total number of channels? That is 6,000. So it will be divided by this, and it comes to be 60 upon 6, that is 10 picosecond per channel. So this is the whole idea, and this is our answer. Okay, I'll write it here. 60 upon 6 is equals to 10 picosecond per channel.